Today, we're going to dive into what is essentially the nervous system for a new kind of AI. It's a set of rules called the Harmonic Communication Protocol, and it's designed to do one thing: keep a super complex artificial mind from, well, completely falling apart. So let's just start with the big question, right? If you're building an AI that's supposed to learn and grow and exist for years, how do you make sure it stays stable? How do you prevent it from just forgetting everything? Or worse, collapsing into total chaos? Okay, so the system we're talking about here is called the lamina continuum. And as you can see, this is not some simple little model. It's meant to be a complex, multi-layered, emotional brain, where you have tons of different modules for things like joy, sadness, surprise, and they're all interacting with each other all the time. And this right here just illustrates the problem perfectly. On the left, you've got the potential for total chaos. When all those different parts are talking to each other with no rules, it's basically like a room where everyone is shouting at once. The goal, which you see on the right, is this elegant, stable system with a memory that actually makes sense. So, how do you get from that chaos to the goal?
Well, that brings us right to our first section. We need to really define the enemy we're up against, the AI's own potential for inner chaos.
The technical name for this problem is structural drift. And you can think of it like this. Imagine one little part of the AI makes a tiny, unrecorded change to another part. Now multiply that by billions of interactions a second. Over time, all those tiny, secret changes start to add up. The system's core structure literally drifts, and that leads to instability, really unpredictable behavior, and even a kind of artificial amnesia.
So if the big problem is chaotic, unstructured communication, then the solution, well, it has to be a clear, universal language that every single part of the system is forced to speak. No exceptions. And that solution is the Harmonic Communication Protocol, or HCP. You really should think of it as the formal nervous system for this AI. It's a really strict set of rules that governs every single interaction, making sure that everything that happens is deterministic, which is just a fancy way of saying it's predictable and, crucially, it's repeatable. And here's the most important principle. HCP's main job is to take all those hidden actions, those secret little whispers between modules, and turn them into explicit, auditable messages. Nothing gets to happen in the dark anymore. Every single interaction is brought out into the open.
Okay, so how does this protocol actually work? To get it, we really have to dissect its most basic unit, which is the message itself. What does one of these messages actually contain?
Now, what's so cool about this is how much information is packed into every single message. It's not just, here's some data. The symbolic payload, yeah, that's the what, the concept being sent. But then you have the reinforcement delta, which says exactly how much stronger or weaker a memory should get. The field delta suggests a change to the system's overall mood or context. The propagation budget, that's a travel limit, a hop count to stop messages from bouncing around forever. And finally, the timestamp, which logs the precise moment it was created. It's a complete, self-contained package of intent.
So, having a detailed message format is one thing, but the real power of HSCP? That comes from the strict rules that actually enforce stability and prevent that structural drift we were talking about.
This slide gets right to the heart of it. In the old, chaotic way, any module could just secretly reach in and mess with the internal settings of another one. It's totally unpredictable and impossible to trace where things went wrong. But with HDCP, that is absolutely forbidden. Instead, one module has to send a formal message to another, proposing a change. It's the difference between total anarchy and a structured, orderly process.
And the source material is completely, 100% unambiguous about this. This rule, this idea of explicit state mutation, it's the absolute bedrock of the entire system's stability. It is completely non-negotiable.
So, what about those propagation budgets we mentioned? Here's a super simple way to see how they work. A message gets sent out with a budget, let's say 3. Every time it gets passed to a new module, every hop, that budget goes down. So it goes from 3 to 2 to 1 and finally to 0. And at that point, the message just terminates. It dies. This is a critical safety valve that prevents a single thought from creating an infinite feedback loop that could just crash the whole system.
All right, now we get to the ultimate payoff. Why go through all this trouble? Why create such a ridiculously structured, deterministic system? The answer is, well, it's incredibly powerful.
Just think about it for a second. We've established that every interaction, every little change, every single memory reinforcement is captured in one of these formal messages. Each one has a precise timestamp, and they're all processed in a very strict order.
And because of that, you can rewind the tape.
The entire history of the AI's internal state, every thought it ever had, every connection it ever made, it can all be replayed perfectly, bit for bit. There is zero guesswork.
This capability has a name, replay debugging, and it's a total game changer. If the AI develops a weird bug or some unexpected behavior, the developers don't have to guess what went wrong. They can literally go back in time to the exact microsecond the problem started and watch the whole cascade of events unfold. It turns debugging this insanely complex system from an art into a science.
So this incredible power, to have a perfect, verifiable history of a synthetic mind, is only possible because of the strict, deterministic rules of the harmonic communication protocol. That's the payoff.
And this all connects right back to the grand vision. By forcing order and preventing chaos, HCP provides the stable foundation you need to build what you're seeing here: sophisticated, long-lived AI agents that can actually maintain a coherent sense of context and an awareness of time, knowing not just what happened, but how it felt and how long ago it happened.
And that really leaves us with one final, pretty big question. If we can actually build an AI that doesn't suffer from this structural drift, an AI with a perfect auditable memory, what new kinds of problems could we even begin to solve?